Okay, the demercuration step. What reagent is used for it and what does it do? Yes.
So the mercury then gets replaced by.
Yeah, so all the NABH4 does, which you can see in this step, is that it replaces this mercurium thing, the HGOAC, with a hydrogen. So you're left with just a plain old alcohol. And it is a Markovnikov addition and there's no stereochemistry. There is technically like kind of an intermediate, but it's not a full carbocation intermediate because it's a partial bond. So it's not a full carbocation. It's this weird like mercurium intermediate. It has its own name, its own properties. So just know it's not the same. Huh?
Does that have to do with backside attack?
Well, the H2O is going to come in and do the backside attack. The H2O or the alcohol. Oh, what's the difference if we're using an H2O versus an alcohol for the nucleophile? Yeah, so H2O produces an alcohol and an ROH, an alcohol, produces an ether. So for the last reaction, what do we think this is called? Yes, it's hydroboration oxidation. And based on the step or the name of the mechanism, what do you think step 1 and 2 is going to do? What does the hydroboration and what does the oxidation? So the BH3-THF is going to do the hydroboration.
The square.
Yes, it makes a square. I'm gonna draw that out, yeah. So what happens with the square?
Ion breaks to.
Yes, it does. It attaches to the boron and what else?
And then the more substituted attaches to hydrogen. I think the bond from the hydrogen breaks to attach to the carbon.
The bond from the hydrogen, from which hydrogen? The one on the BH3?
The one on the beach.
All right, let me just draw this. So we have 2 bonds created on either side of the alkene. Where does the boron go? Where does the BH2 go? And where does the H go? Yeah. So we're going to get BH2 here, right? And then it's going to be partially bonded to the hydrogen on the more substituted side, which makes it anti-Markovnikov. However, Dr. Roche really likes to point out this fact. Technically, this intermediate state is Markovnikov because the delta positive is on the more substituted side. It's not a full carbocation, but in this intermediate square, the delta positive is on the more substituted side. So it's kind of like a pseudo Markovnikov, but the end product is an anti-product. But he just wants you to be aware of that. And I'm just going to draw in the partial charges for this. I don't think you need to know them, but just to be safe. So we get this after the initial attack from the BH3. I don't know what the THF does. I think it's just like sitting there. But anyways, we're going to break this open. We're going to make the partial bonds real solid bonds. So it's going to look like this. Now, what do we do? What do we do with this line 2 of reagents? Yeah, so what does that mean?
Get rid of the spectator and it picks up the BH2 or the OH picks up the BH2.
So the mechanism is really weird and annoying, so we just skip it. But what happens and the final product is, yeah, the BH2 just gets replaced by an OH.
skip that part of the mechanism, you don't need to really know, right? We just need to know that the pH was replaced by.
Yeah, you just need to know what each line of reagents gives you. So I know one thing he likes to do is that he'll give you like the reagents and you think, oh, hydrogenation oxidation, but it won't have the second line. So you have to know that you're going to stop at this product. Same thing with oxymerc and demerc. But the regiochemistry, is it Markovnikov or anti? The overall product is anti, but this transition state is kind of pseudo Markovnikov.
Can you explain one more time, like how it's pseudo, because it looks like the BH2 is still going to the lead substitute.
Yeah, but with a Markovnikov reaction, what happens is the carbocation goes on the more substituted. So because the partial positive is on the more substituted side of the alkene, that's what makes it kind of,
Oh,
yeah.
I got it.
I think I switched that up. Overall anti, is there any stereoselectivity? So for this one, I think this is the only one that does have stereoselectivity. It's going to be a syn addition. So both the hydrogen are either going to be both wedged or both dashed. And what about rearrangements? Are rearrangements possible? Is there a carbocation step? There is no official carbocation step. We have a weird like partial positive thing like we did in oxymercuration, demercuration, but it's not a real carbocation. We can't do rearrangements. Oh, okay. So one more thing that he'll do for this is that this is BH3, right? So you really have to know this step. You kind of have to memorize that because he will replace the H with a hydrogen like isotope like deuterium or tritium, and you have to know like on this what it's going to look like. So when you get instead of the BH3, if he gives you like BD3, then you have to know that this, the H's in this are going to be replaced by a D. So let me just draw that out. If he gives you, yeah, if he gives you BD3 and THF, and then H2O2 and NaOH, the final product is, let me move that. But the final product is going to be this. Yeah, OH and D. So that is very important. You're probably going to get a question like that.
Is there any possibility that it's like a BD2?
A BD2, like in the actual reagent line. BD2.
Is there like a preference between like?
I've never seen that. Because that would ruin like the charge of the boron. So I think you would keep the like the octet the same. Okay, so there's dehydration of alcohols, but I don't think he focuses on that much, so we'll just do it briefly and we won't do the mechanism. And we have to move on, so I'll give you the answer. For this one, this first reaction, if you have like sulfuric acid usually or any acid, it's going to be an acid catalyzed dehydration. So this happens through an E1 or E2 mechanism, which you don't have to know. But basically this oxygen gets protonated, that's the acid catalyst part. If it's an acid catalyst, it usually involves protonating the alcohol to make it a good leaving group. So you protonate the alcohol to get a good leaving group, And then you perform an elimination reaction, which replaces the alcohol with a double bond. Yes,
Would there be a methyl shift in that reaction?
there would be a methyl shift because we have a quaternary carbon over here. I wouldn't worry too much about it, but like be conscious of methyl anhydride shifts, especially for the above reactions that we just went over. Like the, what's it called?
Acid catalyst.
Yes, like acid catalyzed hydration, you have to be very, very aware of the methyl shifts or hydride shifts. I think in one of your homework problems or the extra credit problems, I was looking over it, and then that was like, it was kind of tricky. And you had to know that a few of the reagents would allow methyl shifts, so they wouldn't be the answer. So yeah, thank you. That is something he does like to include.
Is H2SO4 the only thing that'll do the dehydration, or is it anything that dissociates into H plus?
I'm not sure. I know H2SO4 is the most common, but I guess technically you could do it with anything. I've never seen it with anything different though. But the second one is going to be POCl3, and I don't know why I didn't include on here, but it's usually going to be over pyridine, which is just the base. No one really cares about the mechanism for this, but just know that it gets dehydrated through an E1, E2. Just know that if you see these reagents with an alcohol, you could get this as a product.
Is that a major product or minor product? Because that's only, that's substitute.
I think it's the only possible product because that carbon is quaternary.
So there's no, methyl shift or anything for that one?
Doesn't look like it. But anyways, don't worry about these. I'm just including them to like have answers for them. But this question, which of the following would dehydrate the fastest with an acid catalyst? What do you think you would look for with a question like this?
You look at the position of alcohol in terms of primary, secondary, tertiary.
Yes, and then what would the position of the alcohol affect? Yeah, or not really the carbocation. Yeah, overall stability of the conjugate when either the proton or the alcohol leaves.
Is resonance a factor then also?
Yes, resonance is a major factor, which is why E is the answer. Because out of all of the options, E is the only one that has like good active resonance with this benzene. In addition, D, if you remember from last session, this is going to be on the vinylic position, and the vinylic position is not good to dehydrate from because we don't want that charge sitting in the orbital. The sp2 orbital doesn't hold that well. And for B, it's a like primary alcohol or secondary. I think it's primary, but that's bad because if we get a negative charge on this carbon, there's nothing to stabilize it. Like it's just terrible sitting there. With C, if we get that charge sitting on, or any charge plus or minus, if we get that sitting on this tertiary thing, it is more stable, so it's pretty good. And then on A, it's just secondary. It's not that amazing. It's better than B and worse than C. So E is the best because it has active resonance. But we have practice problems. So I'm gonna give you like 5 minutes to do these. Does that work? And then somebody can come up and do it. So you actually like break out to groups and socialize, and if you want to work together on these, and then you can send somebody to write your answer up on the board when you're done. Does that work? All right, so 5 minutes to do these three. Okay, do we need more time? Is anyone ready to come up and do number 1? Yes?
Sure.
All right, go ahead. Here's markers. I guess go on the side.
Okay, so we are doing acid catalyzed penetration for this one. And the important part of that reaction is look for the most, I think, look for the most stable carbocation. So basically you have to pick which bond line form that gives you the most stable. So I went with D2-methyl-2-butanol because that's a butane, that was here, OH is here. When the OH gets cut off and the carbocation forms, it's going to be tertiary, which is the strongest position. Oh, the most stable, sorry.
Yeah, that's perfect. So it is going to be D because that is the only tertiary alcohol. With the other ones, you could do methyl shifts and whatnot, but because D is already tertiary and ready to dissociate, we're just going to go with that one as the fastest. So what's your name?
Caleb.
Okay, good job, Caleb.
Caleb.
Oh, sorry, Caleb.
That, has a water, it's always the old, like, because me, I got thought of it like acid like theatrics or with it into acid that theatrics like a elections. I thought that okay, if there's an alkene like that, what would you use?
Yeah.
I'll learn.
Yeah, I guess you couldn't really look at acid catalyzed hydration for that one. Oh, wait. Sorry, what did you say about the alkene?
Like I kind of did like a retrosynthesis of that. I just thought okay, like this works out because everything else seemed like the OH was going to like be substituted.
Yeah,
So that's how I see it. So
that's definitely interesting. Maybe it like was, I'm not sure if that would apply to all of them. Maybe it would, because if you do it your way, you would get the most stable alcohol.
yeah.
And that's what we're looking for. For the whenever you see like most rapid, you usually look for the most stable position. So if that's a roundabout way to get to the most stable position, then yeah, that's perfect. Okay, number 2. Who wants to try this one? Yes. Oh, they're over here.
So we, so I just saw like, okay, like if you have prevented synthesis of 2-butanol, I just draw that out. So I came up with this. And then from there, I just looked at like every reaction. Basically, I kind of like backwards and draw that's one like 1-butene. Like something like this. So then from there, like I just looked at each and one divided just off memory. Okay, I don't think A would give us, you know, like an OH. Maybe it will, but just maybe like in a different thing, I guess. For B, that's hydroboration, oscillation. So that would give like an anti-electronic OH. So like that would work. And for C, like that's mercury. hydration preparation, which would give a arconic OH. So I'm just gonna put that.
Yes, well, that is one of them. But look at A again. It's gonna be an acid catalyzed hydration, which is also Markovnikov. And in this case, when you see an acid catalyzed hydration, you could be careful, or you should be careful about rearrangements. But in this case, since it's just a simple like alkane that you're making with no methyl substituents, you don't really have to worry about the shifts and all that. So A, because there's no like possible rearrangements, it's going to give you the straight up Markovnikov product. So I think A would work as well here.
Okay. So it'd be D then.
Yes.
Good question. So asking that you want us to butanol and they give us 1 butene. So basically, changing it from the bond to a single bond, basically, right?
Yeah, you're substituting the double bond with a hydrogen and an alcohol. So like this. Yeah. Number 3. Okay.
So this is pretty much like what you said with the deuterium. I can like throw you off. We know it's a syn addition. So we're gonna get an enantiomer too. And that's why, I think that's why there's, it's in excess, right?
It's what?
The BB3 2, it's in excess because we're gonna get an enantiomer.
I don't know about that. I don't know why there's 2 of them.
Yeah, that's what,
I just like accepted it.
yeah, that's what kind of threw me off.
Yeah.
But pretty much we'll get that intermediate step that you're talking about. So it's gonna be anti-Markovnikovs. So we'll do the two. And then it's gonna attach this way, so it's gonna make this square. And like you said, it's syn addition. So it's gonna end up looking like this. Doesn't matter if it's wedged or dashed. Well,
No,
I guess 'cause
as
it's
long as they're
dashed.
both the same. Yeah.
Sorry, Megan, I'm gonna have to erase your arm. Or, yeah, which.
Oh yeah, it is. No, it's not an OD because we have the NaOH. So the only D is going to be in the square on the first step.
Right, okay. So that's what I got.
That
Plus the enantiomer,
yeah. That's
so that's 1.
H. Yep. Perfect. What's your name?
Magnum.
Nice. Yeah, perfect. Did everyone copy that? We should really move on to protecting groups. I'm running a little bit behind. Oh, actually, before protecting groups, so Roche doesn't like talk to me that much, which is an issue because he really should, and he doesn't tell me about stuff that he's including. So which is why we get situations like this where he goes over stuff in lecture and doesn't let me know, so I have to add it last minute. But there's one more reaction for alcohol synthesis. It's called hydrohalogenation. What's going to happen with that? No, it's not halogen, it's halohydrogen formation. My bad. So thankfully there's this massive blank space that we can use to write it in. The reagents for this are going to be X2, X meaning a halogen, over like an alcohol or a water. And then this gives you alcohol, this gives you an ether. So quickly, let me just draw an example reaction. The alkene is going to act as a nucleophile and it's going to attack one of the bromines. Don't worry about why, just it does. And it's going to open up and give you here with the, so you can see arrows, they're kind of forming a triangle. It's just going to form a bond just like that. So now that we have this bromine is taking electron density from these two carbons. So these two carbons are now delta positive. Because they're delta positive, we can take our nucleophile and it's going to come in and attack the more substituted side. It attacks the more substituted side because it's Markovnikov. Let me write that down. So if you have a Markovnikov addition, the nucleophile goes on the more substituted side. So let's take our methanol. And it's going to attack up here in the tertiary position. This is going to open up. And we get this as our product. Okay, and there's one more reaction that he did that I'm gonna have to run through really quickly as well. That was halohydrogen formation. There's one that's very similar. It's hydrohalogenation, except in hydrohalogenation, well, you'll see when I draw it. So you start with an alkene. Your reactions are going to be an HX, so a hydrogen bonded to a halide or halogen. So let's do HBr because that's the most common one. The alkene attacks the hydrogen. You do get let me just write that first. It's Markovnikov, and you do get rearrangements because there's a carbocation intermediate. It's Markovnikov's when the alkene opens up, I should scroll it. The carbocation goes on the more substituted side. So we get that. We get our H attached to the less substituted side. Now we have a bromine ion, which is going to go and attack the electrophilic carbocation. Wait, what was the point of this? Okay, so there's that reaction. Let me just label it. Don't worry about it too much, and I'll also post a study guide. I'll make this much neater, I promise. But yeah, so don't worry, just study that. Be familiar with the reaction, the mechanism. Well, be familiar with the mechanism. Know the products, mechanism, just generally get the idea of it. The important ones are the intermediates for oxymercuration, demercuration, and hydroboration oxidation. Yes.
Can you show that?
Yeah, it's up here.
And like they both would end up on that same carbon.
Not on the same carbon. They end on, like, what do you mean? Both groups that are getting attached?
Yeah. Oh, wait, okay, now I see.
Yeah. Everyone, yeah. Well, this one, there was no rearrangement because this was already the more substituted one, but it is possible, yeah. Okay, so I can move on to protecting groups. So the point of a protecting group is to replace the alcohol with a leaving group, and it just makes everything more reactive. I don't think you really need to know why they exist or what we do with them. Just know the reagents and what they do. So over here, we have a bunch of reagents, and this is a general reaction for them. If you see an alcohol and any of, well, I have to add them because once again, Roche doesn't tell me extra stuff that he does that is not on my worksheets, so we're gonna have to add it now. There's one more reagent in this category, which is ZnCl2. But for this list right here, we're basically just turning the alcohol into a halogen via an SN2 reaction. And do you remember a property of an SN2 reaction? What does it do to stereochemistry? It inverts it. So whenever you get one of these, you have to know that it's going to invert the stereochemistry. So knowing that this is done through an SN2 mechanism, what do you think the answer is to this question? Which alcohol would react most rapidly with PBr? So PBr3 probably. So PBr is in these mentioned reagents. And what mechanism do these react by? Yeah, SN2. So what are we looking for when we have a rapid reaction with SN2? What would react the most rapidly? Yeah, because it's the least sterically hindered. It's going to be the primary alcohol. The rest of them have more bulk around the actual alcohol. Like for example, this is secondary. This one has this methyl that's really close to this carbon where you would attack. And then this one is tertiary, which like would not do an SN2 reaction. Yeah. It's just the presence of this methyl. It's closer to this carbon, the electrophile. And in A, that methyl is farther away. So what is the purpose of a protecting group? It's to keep or change the stereochemistry. So when we're doing reactions, when you want a given product, we probably want with a set stereochemistry. And with using different protecting groups, we can either keep or invert that. So you have that first category of protecting groups, which basically just turns the alcohol into a halogen. Now you're going to have the second category, which is going to glue itself onto the oxygen. So in the first one, you replace. In the second one, you add to the alcohol. I think everyone can see that here. Like this group literally just gets cut and pasted onto the alcohol. It replaces the hydrogen. Oh, and it's important to know what they're named. So this thing, basically this thing is going to stay constant, the SO2Cl in both of these reagents. What changes is the group that's attached to it. So this group, which you probably don't know, is called a tosyl group. So this is a tosylate. But the easy one to know is that this is a methyl. Methyl sounds like methyl, close enough. So we're gonna know that this is our mesylate. And what I do, I just remember like, oh, that looks like the mesylate, so the other one has to be the tosylate. And what these do Basically, the reaction, if you want to know really quickly, the alcohol acts as a nucleophile, is going to attack the center thing. The Cl leaves as a leaving group, and then you get this tosylate or mesylate as your final product. Yeah.
So, in my studies, I realized, how it starts and how it ends. Do we have to know how, like, the entire mechanism, like, its complexity?
No.
Yeah, that shit was very
For some,
intense.
I would be familiar with them. Like, make sure you've looked at them and know the general idea of what goes on. You don't need to know every arrow or like every delta positive. That's a waste of time. But what you should know is the general, like, what's going on. So in this one, the idea is that the alcohol is the nucleophile. It attacks the center sulfur, I guess. The Cl is the leaving group, and then you just get this attached to it.
And then in the end, will be.
Oh.
Is that OH or say dashed?
Yeah, so the really important thing to know is that the stereochemistry when you added the tosylate or mesylate did not change. However, when we used the other types of protecting groups, the halogen, we number one, replaced the alcohol, and number two, inverted the stereochemistry. So basically the tosylate and mesylate is the exact opposite of the first category. That's kind of helpful to know. It's just memorize one, like the properties of one type of reaction, and then just like kind of look at the other ones in relation to it. It's like, how is this reaction different than the one I know? That's how I did a lot of the Orgo too.
No half of it.
Yeah, and then you can just infer the rest.
Yeah.
But if you see this long, messy disaster, look at it for a couple seconds. You'll see that it has the SO2Cl, which is characteristic of the tosyl and mesyl groups. And we also have this like weird, nasty carbon chain. If we have that, it's probably going to be the tosyl because the tosyl has a lot more carbons than the mesyl does. If we had a mesyl, we wouldn't have this. We would just have like a CH3 attached to the SO2Cl. So don't get scared when you see this. That's all there is to it. But considering what we just learned, how do you think this alcohol is going to look when we react it with the tosyl group? Exactly. And then the abbreviation for tosylate is TS. So if you see OTS, which you will see, just know that's what it means. And there's one more step before we get our final product. First of all, did the first step make sense to everyone, how we went from the alcohol to this tosylate? Okay, so in the second step, what do we have? Mm-hmm.
Which will go and kick off the OTS and SN2.
Exactly. So the whole point of adding the TS was to make it a good leaving group. Now it's a good leaving group, so the iodine can come in, attack here, and what's the product going to look like? What happens to the stereochemistry at that carbon? It inverts because it's an SN2 reaction. So we get this as our final product. Okay, and we're out of time. So we'll finish up the protecting groups, I think, tomorrow. In the meantime, I think that was a decent introduction. And if you came late, I'll pull up the sign-in thing again. It's also on the handout, like for your convenience, so you don't have to scan it from the board. No problem.